Titan is the kind of world that makes the solar system feel unfinished. A moon with a real atmosphere, rain, rivers, lakes, and seas. But all of it built from the wrong chemistry, under the wrong temperatures, in the wrong place for life as we understand it. For years, that made Titan fascinating, but easy to keep at a distance. Too strange to dismiss, too alien to take seriously. But James Webb has now looked at Titan's atmosphere and found something that pushes this moon across a dangerous line. Not into proof. Not into certainty. But into the zone where serious scientists can no longer smile at the idea of life and walk away. Because Titan is no longer just weird. It is becoming chemically impossible to explain. Most moons in the solar system are silent, airless, cratered things. Titan has never belonged in that category. It carries a thick nitrogen atmosphere, denser than Earth's, with weather systems, clouds, river valleys, lakes, and seas. But on Titan, the role of water is played by methane and ethane. The moon runs an alien version of Earth's hydrological cycle, where hydrocarbons evaporate, condense, fall as rain, and carve paths across the landscape. That alone made Titan extraordinary. This was not just a frozen object drifting around Saturn. It was an active world, a place where chemistry and climate interact across long stretches of time. And because sunlight constantly breaks apart methane high in Titan's atmosphere, that atmosphere keeps producing more complex organic molecules. Those molecules drift downward and coat the surface, building a global layer of prebiotic material. Titan is not sterile in the chemical sense. It is soaked in organics. And that is what made it so difficult to categorize. Not Earth-like, but also refusing to behave like a simple dead moon. It had atmosphere. It had weather. It had organics and a surface shaped by flowing liquids. Long before James Webb ever looked at it, Titan was already sending the solar system a dangerous message. Habitability might not look the way we expect. What James Webb brought to the story was not a landing, not a rover, not a camera-catching movement. It brought precision. Webb used infrared observations to study Titan's atmosphere in enough detail to identify molecules and spectral features that force harder questions than ever before. Among the signals were compounds connected to increasingly complex organic chemistry, the kind that on Earth belongs upstream from the molecules life depends on. That alone would have been enough to make Titan more interesting. But then came carbon dioxide. In a place where the atmosphere's chemistry should push carbon in completely different directions. To detect carbon dioxide in those concentrations means either chemistry is happening that we don't yet properly understand, or there is some source process our old picture of Titan never captured. And then there is the unidentified signature. A lower atmosphere spectral feature that does not match any clean entry in current molecular databases. Scientists handle that kind of result carefully, because unknown does not automatically mean biological. But it does mean the chemistry is richer, stranger, or less complete in our models than we thought. Titan is not handing us an answer. It is removing our right to keep pretending the old atmospheric story was finished. What makes Webb's findings so powerful is that Titan was never a clean slate going in. Earlier observations had already uncovered anomalies that made astrobiologists deeply uncomfortable. Hydrogen appeared to be flowing down through the atmosphere and disappearing at the surface faster than expected. Acetylene, a compound that should have been present in abundance, seems strangely depleted near the ground. These are not trivial details. They are the kind of imbalances that immediately force the question: is some unknown process consuming energy-bearing molecules? That alone was not proof of biology. Responsible scientists never said it was. But it created an uncomfortable pattern. If you imagined a methane-based metabolism operating on Titan's surface, one that consumed hydrogen and acetylene as inputs. You would expect exactly those anomalies. Again, not proof. But no longer the kind of result you can dismiss as fantasy. Now Webb adds new atmospheric anomalies on top of those older surface imbalances. Different spacecraft. Different years. Different instrument. At some point, Titan stops looking like a world with one or two oddities and starts looking like a place where the chemistry itself keeps drifting into biologically suggestive territory. That does not mean life is there. It means the burden of explanation keeps rising. The most radical thing about Titan is not simply that it may host chemistry relevant to life. It is that if life exists there, it may exist in a form so alien that everything Earth taught us becomes a liability. On the surface, Titan is far too cold for liquid water. Water there behaves like rock. The flowing liquids are methane and ethane. Any life on Titan's surface would not be water-based biology in any familiar sense. It would be a cryogenic chemistry system operating in a hydrocarbon solvent, with completely different molecular strategies for membranes, energy, and survival. That sounds impossible only because Earth trained us to think one way. But Titan has long been the place where scientists quietly test whether life truly requires our version of habitability, or whether nature is capable of stranger experiments. And Titan may go even further. Because beneath its icy shell, gravitational data suggests the existence of a subsurface ocean of water and ammonia. That means Titan may not offer one possible habitable environment, but two. A hydrocarbon world at the surface. A water-rich one below. And that is why James Webb's result matters so deeply. It pushes Titan out of the category of chemically exotic curiosity and into the category of serious challenge to our assumptions. Titan is no longer just asking whether life exists there. It is asking whether our definition of where life can exist has been too small all along. One of the most unsettling ideas about Titan is that it may not have one potentially habitable zone, but two. On the surface, methane lakes, hydrocarbon rain, nitrogen air, and an endless drizzle of organic chemistry falling from the sky. Beneath the crust, a hidden water ammonia ocean in contact with deeper rock. That means Titan could be hosting two radically different chemical environments at the same time. One cryogenic and methane-based above. One darker and potentially water-based below. That is an extraordinary possibility. It means Titan is not simply a candidate for one strange form of life. It may be the only place in the solar system where nature had the opportunity to try two entirely different routes toward biology on the same world. If surface chemistry ever crossed the line into methane-based metabolism, that alone would rewrite astrobiology. If the deeper ocean supports water-based chemistry near rock interfaces, that would make Titan a second kind of ocean world target, layered beneath the first. And that is why Titan feels so dangerous scientifically. It is not just weird. It is multiply weird. A world where the surface and the interior may each be asking a different version of the same question. Under enough time, enough chemistry, and enough energy imbalance, does nature keep trying to become alive? This is where the story stops being observational and becomes confrontational. NASA's Dragonfly mission is designed to land on Titan and then fly from site to site like a rotorcraft explorer, directly sampling the surface chemistry of one of the most provocative worlds in the solar system. That alone tells you how seriously Titan is being taken now. Dragonfly is not being sent because Titan is visually beautiful. It is being sent because Titan's chemistry has become too important to leave unresolved. By the time Dragonfly arrives, it will not be flying into a simple mystery. It will be flying into layered evidence, atmospheric anomalies seen by Webb, older hydrogen and acetylene imbalances from previous spacecraft, decades of organic chemistry, and a moon whose surface may already be behaving in ways that demand explanation. Dragonfly's job is not merely to admire Titan up close. Its job is to test whether the chemical strangeness we have seen from afar survives direct contact. And maybe that is the deepest reason James Webb's result feels so significant. Because it did not solve Titan. It made Titan urgent. It turned a world that once sounded like an exotic side story into one of the most serious habitability puzzles in the entire solar system. Dragonfly is not going there to ask whether Titan is interesting. That question is already answered. It is going there to ask what kind of world could produce this many biologically suggestive signals, without crossing the line into something alive. So in the end, what makes James Webb's discovery feel so impossible is not that it proves life exists on Titan. It is that it makes the old comfortable dismissal so much harder to defend. Titan already had the dense atmosphere, the methane rain, the rivers, the lakes, the endless organic production. Webb has now added new atmospheric clues that make that chemistry impossible to call routine. And when those clues are placed on top of the older anomalies, the missing acetylene, the disappearing hydrogen, the unexplained lower atmosphere signal, the pattern becomes very difficult to wave away. That is why this changes everything. Titan no longer looks like a strange frozen moon that just happens to be chemically interesting. It looks like a world actively testing the boundaries of what habitability